Hey everybody, I hope you are doing well. I am going to switch my pointer to a pen that will hopefully allow me to write on my PowerPoint so that as you are taking notes, you can fill in. Notice that I put all of the notes for the whole unit in one place. My thought was try to help you keep them organized a little bit, and we'll just do short videos to fill them in. So today I'm going to look at isotopes and atomic mass, and let's see how that goes. So you're familiar with this. I don't think I need to belabor that you have a proton, a neutron, and an electron. I think you know that protons and neutrons are in the nucleus. I think you know that electrons are in the electron cloud or the energy level. Hopefully you also know that the proton and the neutron contribute to the mass of the atom. But what specifically we're going to look at first is that the number of protons determines what the substance is. That's how we identify the elements on the periodic table. And so if you haven't done so already, at some point today, you want to make yourself a printed copy of the periodic table that I posted in this unit. The other thing that's significant is electrons have virtually no mass. They are about 1/2000th the mass of a proton. So electrons don't contribute to the mass of the atom at all. It'd be like you taking, 2 or 3 hairs and yanking them out of your head and then getting back on the scale. You wouldn't see any kind of change on the scale. So let's just kind of do a thought experiment. If we had a proton and that proton was actually the size of an orange, just a navel orange, just, the one you'd peel and you'd eat. That's about 10 centimeters in diameter. And so the actual size of a proton is 10 to the negative 15th. It is very, very small. We can see it with electron microscopes, but it's not anything that we can see with the naked eye. So to make it kind of relative for us, we're going to say that a proton is the size of an orange. Well, a neutron would also be the same size. So a neutron would also be the size of an orange. And the electron is 0.1 centimeters. So if you took that distance of 10 and you broke it into 100 pieces, one of those pieces would be the electron. That would be the equivalent of taking the orange and slicing it 100 times. So it actually would end up being 1 bite of one orange. Let's go ahead and fix that. That's 1 bite of one orange. So overall, the atom would be the size of an orange, okay, if you had one proton in it like you do with hydrogen. Now, if you had an atom that had lots of protons, lots of neutrons, you start putting all of those oranges together. It might look like a bag of oranges, okay? So the model of the solar system most people think about is the model of the atom that most people think about is the solar system, with our nucleus, the middle, and then we've got these rings around the atom that are where the electrons live. So just kind of go with that model. The thing that we kind of get trapped at, and we talked about it a little bit with the quantum mechanical model, is that, when Rutherford proposed this kind of model, he was thinking two-dimensionally, like everything was flat. And now we understand that that's not the case, that the electrons actually orbit in a spherical pattern around the nucleus, not just a flat sheet. Okay, so there's more of a three-dimensional aspect to it that some of us are better, not me, some of you are better at seeing 3 dimensions on paper than I am. So mass is from what's in the nucleus, the protons and the neutrons, and the size of the atom is because of the electrons' radii. How far away are they orbiting that nucleus? So the atomic number is the one that appears on the periodic table. This is a screen capture from your periodic table that hopefully you will download and print for yourself at some point. The atomic number can appear in different places on that periodic table. Sorry, I realize I'm talking really fast, so I'm going to slow down a little bit. the number can move to a different location, but the significance of it stays the same. And that is that the atomic number represents the number of protons in that nucleus. So if we're looking at nitrogen, we know that there are 7 protons in that nucleus. If we look at sulfur, we know there are 16. If we have a neutral atom, the number of protons and electrons will be the same. So that being the case, we could say, well, an atom of phosphorus has 15 electrons. So the atomic number gives us the number of protons, and if it's a neutral atom, it gives us the number of electrons as well. So we would say that hydrogen has how many electrons? 1. And we would say that hydrogen has 1 proton. Magnesium, you'd have to get your handy dandy little periodic table here. I don't know if this is going to show up backwards or not, but magnesium is right there, and that number is 12 if it is backwards. I still need to figure that part of this out, which is why I'm doing this video first. Most of it I will be doing on the screen. So magnesium has an atomic number of 12, therefore it has 12 protons, it has 12 electrons. So I'd like you to pause the video and try the next 2 that are on your sheet. Pause the video. Oh, never mind. I should have had the text box pop up later. So I need to fix that for next time. Oh well. Be flexible with me, right? We're all learning. This is my first video to post for you guys to do, so we'll get it straight. I'll get better, I promise. All right, so mass number is not equal to atomic mass. Those are 2 different ideas, and we're going to talk about each one individually. So mass number is the number of protons plus the number of neutrons. The unit is going to be the atomic mass unit, and this is going to give us an idea of the mass of an isotope. One of the specific atoms is going to have a definitive or a discrete number of protons and a discrete number of neutrons. The atomic mass, here's the definition, and we're going to come back to it, but atomic mass is a weighted average of the known isotopes of an element. Well, I keep saying this word isotopes, so let me define it for you. Isotopes are different variations of one element. So we could have 3 atoms of carbon, and one of those atoms of carbon would have 6 protons and 6 neutrons in the nucleus. The second atom would have 6 protons, same number of protons because it's carbon, and 7 protons in the nucleus. And carbon 14 would have a nucleus with 6 protons and 8 neutrons in the nucleus. So different number of neutrons, same number of protons. Very important to understand that that is the case for an isotope. Okay, because we have different number of neutrons, we get different mass numbers, because if you recall, the mass number is equal to the number of protons plus the number of neutrons. Okay, so if you look at oxygen on the periodic table, you would see that oxygen has an atomic number of 8. So that means we have 8 protons and 8 electrons. The mass on the periodic table that I'm looking at is 15.9994. So we're going to say that's 16 for right now. We'll get to why we don't really do that, but we're going to say that it's 16 as a mass number. So if we have a mass number of 16, we can figure out how many neutrons that is by taking 16 minus 8, the mass number minus the number of protons, and we would get 8 electrons for that. Okay, so this is what we would write this as. This is what we would call an isotope symbol. P stands for phosphorus, and each one of these parts has a specific meaning. So let me talk about what each one of those means. So the top number in your isotope symbol is going to represent the number of protons and the number of neutrons added together. The bottom number here is the number of protons only. Now, the number of protons is defined by what element it is. So it is also appropriate to just write that. You can leave out that Z number, the zenith number, because with me telling you that it's phosphorus, I am by default also telling you 15 protons because all phosphorus atoms have 15 protons. So this piece of information will tell us that we have 15 protons. We know we have 15 electrons because it is a neutral atom. The reason I know it's neutral is there is no charge. In this box right here, you would write a charge, and we'll get to that later. Okay. And then neutrons, I would take 31 minus 15 and figure out that I have 16 neutrons. Okay. So we're not going to do all of these. We're going to practice a few of these together. So I have silicone is 14. Because the atomic number is 14, I know I have 14 protons and 14 electrons. To get the mass number, I'm going to add protons and neutrons together. So I know I have 29. This is silicone or silicon, depending on how you want to say it. And then to get the isotope name, you're going to put a dash and then the mass number. To write the nuclear symbol, we're going to put the symbol for the element, and we're going to put the mass number in the upper left-hand corner. Okay? So let's take a look at this guy. Krypton 84 is our isotope name, so we know it's krypton. I know that the mass number is 84. The number of neutrons is 48. I have two choices to figure out the atomic number. I can look krypton up on my periodic table. If you know the symbol, they're much easier to find. Or you can take 84 minus 48. Either way will get you to 36 is the atomic number, which is the number of protons, which is the same number of electrons since we know we have a neutral atom. And to write the symbol, we put our symbol with the mass number in the upper left. The last one we're going to do together is this bottom one. So we know that Xe, you may or may not know, Xe stands for xenon, but we know that's the element. Because they gave us the 54 right here, we know the atomic number is 54. I don't even have to look at my periodic table. My protons is always the same as my atomic number. My electrons for a neutral atom are the same as my protons. You say, Mrs. Pogue, you keep saying that. You keep saying that. Yes, I keep saying that because we're going to get to these things called ions where protons and electrons are not the same number. And that's going to change the symbol just a little bit. I'm going to skip neutrons for just 1 second. Mass number is 131. The name would be xenon 131. And then I would have to take 131 minus 54. And I know most of you are probably reaching for your calculators, but we can actually do the math without using a calculator. I know, that's mind-boggling. You are allowed to use a calculator for everything in this class, so you don't have to do the math by hand, but it's always good to brush up on those skills. Now, the atomic mass is something different. The atomic mass is the weighted average, as I said. What a weighted average does is it gives extra oomph, if you will, to the atoms that are most abundant. So if I have 100 atoms of chlorine, if I have 10,000 atoms of chlorine. Let's use the numbers that we've got here. If I've got 10,000 atoms of chlorine, 7,577 of them are going to be chlorine 18. Chlorine with 18 neutrons. 2,423 of them are going to be chloron with 20 neutrons. Well, what that means is that 75% of chlorine is the lighter one. So the average mass would be closer to the lighter one. All right. Think about it this way. If you were, I don't know, let's say we were called into Mr. Diggs's office. He's the new assistant principal over CGS. And it was your word against mine. Well, who are they going to take as being the bigger authority? Probably me, right? Or if I get called into the principal's office versus Mr. Diggs, who are they going to take as the authority? Probably Mr. Diggs. So it's sort of like, well, you could take the word of a 5-year-old, but you're probably going to get a better story out of the 15-year-old. But if you're taking a 15-year-old versus a 30-year-old, maybe the better story comes from the 30-year-old. You know, my brother was always the one that my parents believed, and they never ever believed me. And that had nothing to do with anything other than I think he was older. So maybe you're in that circumstance where, you know, your parents always believe your big brother or big sister. I digress. But you guys know I do that a little bit. So how are we going to determine a weighted average? We are going to take the percent and change it to a decimal. So I'm going to take 75.77% and make it a decimal. I move the decimal to the left 2 times, just 2, divide by 100. And I'm going to multiply by the mass number. So chlorine has an atomic number of 17, which means my mass number for the lighter one is 35. I take the percent, 24.23%, and I multiply it by the mass of the heavier one. Now, we could do the math in our heads, right? But you guys aren't doing that. So I'm going to do this super quickly on the calculator, and we're going to get an average atomic mass of 35.48. The unit is AMU. We have no naked numbers in chemistry. Everything has to have a unit. Okay? We'll do one more. So I have carbon 12. That's the mass number, remember? So 98.9% of carbon atoms are carbon 12. So I take that and I make it a decimal, 98.9890. I'm going to multiply it by 12, 12.00000 atomic mass units. Plus, I would then have, well, only 1%. So be careful, 0.011. Make sure you keep that 0 in there. Gosh, that looks like a 7. I'm sorry, that's a parentheses. Times 13.00335. Now, where did these crazy numbers come from? Well, as our technology has gotten better, we're actually better able to measure those little tiny 100,000ths of a gram. I mean, we're literally talking about things the weight of your hair. In one of my chemistry courses, we had to be super careful not to leave fingerprints on anything because the oil in the fingerprints would throw off our results enough that we would actually get the wrong answer, if you will, in the lab. We would be analyzing the wrong thing. So we type it in, and our calculator says 12.01103,685. Okay, that's how many AMUs we have for carbon. If you have any questions on this stuff, oh, real quick, I think I didn't say it, but that's where these numbers come from on the periodic table. The atomic mass is this weighted average of the isotopes of an individual element. So the closer it gets to like 14, you see nitrogen's 14.006. What that tells us is that almost all of the nitrogen that we find is nitrogen 14. Whereas oxygen, almost all of the oxygen we find is oxygen 16. So the ones where we have like chlorine 35.5, well, it means we kind of have an equal balance between two, right? Or we have two isotopes that have like this, two isotopes that are apart by 2 neutrons. So we know that it's closer to the smaller one. Okay. All right. So if you have any questions, email me, and I will see you next time.